This video is about the MM1 Infinity queuing model. So it's the queuing model with inter-arrival times that are exponentially distributed with parameter lambda. Service times are also exponentially distributed with parameter mu. And because we have one server, the service rate mu I is the same for all number of customers in the system. So if you have only one server and if there are multiple customers in the system, then still only one customer can be served at a time. So that's why the service rates are constant. We have infinite queue capacity, and here in the flow diagram you also see that the service rate is the same for any number of customers in the system. We have the utilization rho, and that's lambda over mu. And this rho should be smaller than 1, because if lambda is larger than mu, we have more incoming customers than customers that can be served, and then the system basically explodes. So then the queue length explodes. So we should have a rho smaller than 1 in order to be able to serve all incoming customers. We would like to determine the steady state situation for this queuing model. So we basically would like to know what the probability is that there is no customer in the system at some points in time. That's P0, P1, P2, the probability that there are 2 customers in the system, P3, and so on. So these probabilities are the steady state probabilities, and based on those we can calculate the performance measures for this queuing model. We can calculate those probabilities by using the global balance principle. So if we cut this flow diagram into 2 parts, then the flow from the left to the right should always equal the flow from the right to the left. In this case, the flow from the left to the right is lambda times P0. From the right to the left is mu times P1, and those two should be equal to each other. If we divide both sides by mu, then we have P1 in terms of P0. So P1 is rho times P0. We can do that wherever we like, so we can also do it over here. Flow from the left to the right should equal the flow from the right to the left. That allows us to write P2 in terms of P1. So P2 is rho times P1, and P1 was rho times P0. So that means that P2 is rho squared times P0. So you see that each new term Pi plus 1 is rho times the previous steady state probability. And that implies that Pi can also be expressed in terms of P0. So Pi is rho to the power I times P0. So if we have P0, we basically also have all the other steady state probabilities Pi. And now we need to find the value for P0, and that value can be found by realizing that the sum of all probabilities should be equal to 1. So if we do that, then we can show that P0 will be equal to 1 minus rho. We are going to write down the summation over all probabilities, and that should be equal to 1. We have already seen that Pi can be written as rho to the power I times P0, so this should be equal to 1. P0 is a constant that can be written in front of the summation, so then we get this, and should of course be rho to the power I. This should be equal to 1. And then here we have a sum of a geometric series. The geometric series converges to 0. And the sum of such a geometric series is 1 divided by 1 minus the factor. The factor is rho. So then this is what we will get. And if we then multiply both sides of this equality by 1 minus rho, we will find that P0 is 1 minus rho. So that was indeed what we would like to show. So now we have P0, it's 1 minus rho, and then you can plug that in over here. So then you get that Pi is this. So rho is basically lambda over mu, and based on that you can then calculate all steady state probabilities Pi. Based on that, or first now an example. So let's consider an MM1 infinity queuing model with a mean inter-arrival time of 10 minutes and a mean service time of 6 minutes. In this situation, we would like to calculate the probability that an arriving customer can be served immediately. And we would also like to calculate the probability that there are at least 3 customers in the system at the moment that a new customer arrives. So let us first write down what we have. So we have a mean inter-arrival time of 10 minutes. And the first thing that we need to do is to choose time scale. So you can do everything in hours. You can also do everything in minutes. If we do everything in hours, then we have the arrival rate. So we have mean inter-arrival time of 10 minutes. So per hour we have 6 customers arriving. And we have a mean service time of 6 minutes. That means that we can serve 10 customers per hour. So mu is equal to 10. Rho is equal to lambda over mu, and that's equal to 6 over 10, or you can say it's 3 over 5, but it's smaller than 1. That's what we need to have. And then we can calculate the probabilities. So we can start, for instance, with we would like to have the probability that an arriving customer can be served immediately. That probability is P0, because P0 is the probability that there are no customers in the system. And this is equal to 1 minus rho. So this is equal to 1 minus 3 over 5 is 2 over 5, or you could also say that it's 40%. And this is the probability that an arriving customer can be served immediately, because arriving customers see time averages. That's the pasta property. And the pasta property is valid here because we have exponential inter-arrival times. So the pasta property is also important to mention if you answer this problem. So based on the pasta property, we can say that the probability that an arriving customer can be served immediately is 40%. Then the second question is to determine or to calculate the probability that there are at least 3 customers in the system when a new customer arrives. So here the pasta property is again important, and then the probability is P3 plus P4, because the question is at least 3 customers, plus P5 and so on. This will also be a geometric series, so you can solve it like this, but you can maybe also realize that this is the same as 1 minus the residual probability. So the probabilities that are missing are P0, P1 and P2. So this is an easier way to solve this problem. We already have P0 that was equal to 2 over 5. And then P1 is P0 multiplied by rho. So it's times 3 over 5 gives you 6 over 25. And then P2 will be 18 over 125. This can be written as one fraction, gives us 27 over 125. And that's 0.216. So this is the probability that at the moment that the customer arrives, that there are at least 3 customers in the system. You can write it like this, but you can also say it's 21.6%. So that's an example of an MM1 infinity queuing model. It's also interesting to evaluate the performance measures. So for instance, the expected number of customers in the system, it's equal to this. And we have our expression for Pi. So Pi is rho to the power I times 1 minus rho. And now the question is, how can this be evaluated? It's not a geometric series, but we can still write the 1 minus rho in front. And then we can use kind of a trick to evaluate this summation, because we write 1 minus rho in front, and we also write 1 rho in front, an additional rho. And then we get rho to the power I minus 1 left. And then you maybe see that this is the derivative of rho to the power I. with respect to rho. And if we realize that, so if we write this like that derivative, then you basically get rid of this I here in front. That makes it complicated to evaluate this summation. So we are going to say that it's the derivative of rho to the power I. Now we have a sum of derivatives is the same as the derivative of the sum. So we can basically interchange these two. So then we get this. And then here we have again a summation of a geometric series that is equal to 1 over 1 minus rho. And then the only thing that is left to do is to determine the derivative with respect to rho of 1 over 1 minus rho. Can be convenient then to write it like 1 minus rho to the power minus 1. And then we can use the chain rule. So we write the minus 1 in front, we subtract 1 from the power, and we multiply by the derivative of the inner part. So that's minus 1. And then the minus sign in front cancels out against the minus 1. So then we get 1 minus rho to the power minus 2. Or you can also say that it's 1 over 1 minus rho to the power plus 2. So that is what we now plug in over here. And then what we then get is this. And then you see that we have 1 minus rho divided by 1 minus rho. So we only have 1 minus rho left only once in the denominator. And we can also bring this rho to the numerator. And then this is our final expression. So this is the expected number of customers in the system for an MM1 infinity queuing model. So only valid if there's no maximum queue length. Then also a special property of an MM1 infinity queuing model is that the total time that a customer spends in the system is also exponentially distributed. So a customer arrives, there can be no waiting time or there can be some waiting time, and then there is also some service time. The sum of those two is also exponentially distributed, but then with parameter mu minus lambda. We will now consider the same example again. So again, the MM1 infinity queuing system with 10 customers arriving per hour. Sorry, with 6 customers arriving per hour. So the inter-arrival time, mean inter-arrival time is 10 minutes, and the mean service time is again 6 minutes. And we are going to calculate the probability that the customer spends more than 15 minutes in the system. So that is the sum of the waiting time and service time. And we are also going to calculate the mean queue length. So maybe good to write down what we still have. So we still have that lambda is 6 and that mu is equal to 10. Both are in hours. And we also still have our rho is equal to 3 over 5. And now we are going to write down what the distribution is for the time in the system. So we say that the time in the system is denoted by capital T, and the total time in the system is exponentially distributed with parameter mu minus lambda. So it's exponentially distributed with parameter 4. And we would now like to find the probability that the time in the system is larger than 15 minutes. Because we have expressed everything in hours, 15 minutes is 1 over 4 hours. The probability that t is larger than 1 over 4 is 1 minus the probability that t is smaller than 1 over 4. And this is now the distribution function of the exponential distribution in the points 1 over 4. And what was the distribution function of the exponential distribution? That was equal to e to the power, 1 minus e to the power minus the parameter. So the parameter is alpha times t. And in our case, the parameter value is 4. So what we now get is the following. It's 1 minus and then the distribution function evaluated in the point 1 over 4. The parameter alpha is 4. So then this is the probability that the time in the system is larger than 1 over 4. You see that we have 1 minus 1 that cancels out, and we have minus minus e, so that becomes plus e, and then e to the power minus 4 times 1 over 4, so that's just minus 1. So this is the probability. It's the same as 1 over e, and we can also give an approximation by using a calculator, 0.368. Of course, we are talking about a probability, so it should always be in between 0 and 1. If you like, you can also use 36.8%. So this is the probability that a customer is more than 15 minutes in the system. The second question is to determine the mean queue length. So we have our formula for the expected number of customers in the system. That was rho over 1 minus rho, and that is equal to 1.5. And based on one of Little's formulas, we have that Ls is equal to lambda times Ws. So that means that Ws can be calculated based on Ls. So it's Ls divided by lambda. If we divide 1.5 by 6, then we get 0.25. This is the expected time in the system. And because we talk about time, we should then also indicate the time scale. If we have the expected time in the system, and if we subtract the mean service time from that, then we get the mean time in the queue. So it's Ws minus the expected service time. So it's 0.25 minus the expected service time is 6 minutes. So that's 0.1 hours. So that gives us 0.15. So this is the expected time in the queue. And then based on the second Little's formula, we can now say that LQ is lambda times WQ. And LQ is what we're interested in because LQ stands for the mean queue length. So it's 6 times WQ, 6 times 0.15 is 0.9. So the mean queue length is slightly below 1, it's 0.9, so on average there are 0.9 customers in the queue.